Our next speaker is Richard Allen of UC Berkeley. His PhD at Princeton, I believe. Owes everything, I'm sure, to his postdoc at Caltech. And he's now the director of the Seismological Laboratory here. Please.
Great, thank you. So it was interesting listening to Harvey's talk. You know, in seismology, we used to think of ourselves as being big data users, and it's impossible to make that statement following the talk that we just heard this morning. We are very small data users, I guess. But I think what I want to talk about, what I want to emphasize, is the fact that because we are now starting to collect a lot more data than we were, we're sort of starting to try and think about other ways of analyzing the data, much like Harvey was talking about, and about using various machine learning techniques in order to do that. And I am not the person that knows how to do that, so I'm just going to put our problem in front of this group, and I'm hoping that somebody will figure out how to help us do a much better job than we are currently doing. So I'm going to talk about what's sort of a new effort in seismology to provide warnings. Earthquake early warnings. And I'm going to talk about it in two contexts. One is what we're actually already now doing today, which is using traditional seismic networks. But then I want to talk about what I think is coming along, which is sort of massively more data, very noisy data, the usual kind of characteristics that I'm sure this group hears from a lot of people. Okay, so when I talk about warnings when you need them in the context of earthquakes, I guess I'm not sure, maybe half the people in the room are from the West Coast and half of the people in the room from the East Coast. So for those who are in the East Coast, this is what we're concerned about. So we are concerned about earthquakes, obviously, up and down the West Coast. We're very fortunate in this country that we have building codes that mean that buildings should not collapse. So if we have an earthquake while you're here this week, you're unlikely to die, is the good news. The catch is that the insides of the buildings are not necessarily built to similar kinds of standards. And I have to say, when I look at the ceiling tiles for this particular room, it's particularly alarming. And so when we talk about warnings, when you start to feel shaking, what you should be doing, a quick recap for earthquake safety, if the ground starts to shake, you get down behind the chair in front of you. And the reason is that these ceiling tiles are going to fall down. If they hit you on the head, they could do you some serious damage. So when we're talking about warnings, we're talking about using a few seconds to take protective measures so that you don't get injured in an earthquake. So this would be one example. This is another example closer to home. We had an earthquake in Napa almost 2 years ago, I guess now, and it was a small earthquake. It was only a magnitude 6. There was one fatality. But things like this, fireplaces falling down. So we know how to build buildings that don't collapse, but still we get a lot of injuries, and we expect to get a lot of injuries in earthquakes, and that's one of the applications of warnings. Going to other parts of the world, this is Nepal. Last year in Nepal, of course, other parts of the world do not have the building standards that we're fortunate to have here. And so you get much wider spread damage and much larger number of fatalities. And again, having warnings, in the case of Nepal, we estimate they could have had about 20 seconds of warning in Kathmandu for these earthquakes in Nepal. Taiwan, even places that have really good building codes, Taiwan has excellent building codes. They don't always do their job, as you can see here. And so just increasing people's awareness of the hazards associated with earthquakes is another piece, and that ties in to using mobile technology to provide the warnings. It also provides an opportunity to educate people about this. And finally, it's sort of miraculous the number of scenarios when people could use a warning when there's going to be an earthquake. This is damage to the road from the Napa earthquake. Of course, aftershocks are very common after earthquakes. Aftershocks move the same fractures that were caused by the earthquake. This is a really foolish thing to be doing immediately after an earthquake, just in case you didn't know. Okay, so those are just to give you some example of the warnings that we're talking about. As I mentioned at the very beginning, I want to do a two-pronged approach. I want to start by talking about Shake Alert. Shake Alert is what I'll call a proven technology. This is using traditional seismic networks to deliver warnings, and we're getting very close to having a public warning system on the west coast of the United States. So I want to introduce the topic by giving a quick overview of what Shake Alert is about. But most of the time I'm going to spend talking about a new effort that we have to use smartphones to actually record earthquake shaking. So using the sensors on the smartphones to record shaking. We're interested in doing it to generate a whole new sort of global seismic network to collect data for all kinds of research. But why should you put the app on your phone? Well, one reason would be because that way you'll get earthquake early warning. So the objective of MyShake is to collect data for all kinds of research. But one of those pieces is earthquake early warning, and that's why we believe many people will put the app on their phone. Okay, so what is earthquake early warning? Just to give you a slightly better sense of the amount of time we're talking about. This is a real-time cartoon of the most damaging earthquake for us here in the San Francisco Bay Area. This is going to be a magnitude 8 earthquake on the San Andreas Fault. It started up here. This brown swath is the actual rupture, then it's going to come all the way down the San Andreas Fault, past the Bay Area, and stop right about here. The circles are the energy that's radiating out from the fault during the earthquake. The yellow circles are the P waves. They travel fastest, okay, so they arrive first, but they don't have very much energy associated with them. So right about now is when we would feel the first P wave. And this is a big earthquake. We would feel it. We would all look at one another and we would wonder what's going on. After a few seconds, we would know this is an earthquake, but we would assume that this is a moderate-sized earthquake somewhere in the Bay Area. We would have no idea it's just the P wave for what is a truly massive earthquake. It's only when the S waves, represented by the red circles that travel about half the speed, it's only when the S waves start to arrive that you start to see strong shaking. So now is when we would know that this was really a very large earthquake, and if you weren't already on the floor, you would all be on the floor by now and wondering what was going to happen next. But still, the strongest shaking hasn't started. Okay? The strongest shaking here in Berkeley will occur when the fault ruptures closest to us. So this is the section of the fault that's closest to us. So it's only when this rupture occurs right here that we would start to feel the very strongest period of shaking. It's more than 2 minutes after the beginning of this particular earthquake. Again, this is running in real time. So this just illustrates that there's actually a lot of time during the course of an earthquake, okay? And that's the time that we want to take advantage of in order to provide earthquake early warning. But clearly to do that, we have to be able to process whatever data we have in real time very rapidly in order to push warnings out to people that might be in harm's way. Right now is when the strongest shaking would be starting right here, and the strongest shaking is going to go on for about another 30 seconds or so before it's done. Okay, so this is the worst case earthquake for the San Francisco Bay Area. It also happens to be the best case scenario in terms of the amount of warning time, as in the maximum amount of warning time. Maybe a minute and a half worth of warning is what we might expect for this event. More realistic estimates of warning times for the more frequent earthquakes that might occur close by are seconds to tens of seconds. Okay, the amount of warning time is a simple function of our distance from the epicenter of the earthquake. If the earthquake starts closer by, there's less warning time. Okay, so that's the idea behind earthquake early warning. Yeah?
How does the 1989 quake compare with what you just showed?
Yeah, so if I go back, the 1918, yeah, and please do stop me with questions, because, yeah. So the 1989 earthquake, the Loma Prieta earthquake, which was the last sort of major damaging earthquake here in the Bay Area, ruptured this section of the San Andreas Fault right here, okay? It was a magnitude 6.9 earthquake. It's about 100 kilometers from San Francisco, Berkeley, Oakland area. And so with about 100 kilometers and the system I'm going to show you, you'd have about 20 seconds of warning. So that's what we'd get in a repeat.
Are the rates of the P waves and S waves physical constants that are uniform for all earthquakes?
Yeah, so the P and S waves, the P waves travel at about 6.5 kilometers per second. The S waves travel at about 3.5 kilometers per second. Of course, they do vary slightly. It depends on the subsurface conditions, but only small amounts. Yeah, so that's right. So that's fixed. So predicting when the shaking is going to arrive is easy. Right? The challenge is recognizing when the earthquake starts and doing it very quickly. So using as little data as possible to know that there's an earthquake and estimate the size of the earthquake as accurately as possible. Those are the challenges. Yeah.
How likely is this for now? You tell us that you know a day ahead there will be an earthquake. Or do you have some lower bound that this is in principle impossible?
Well, I won't say it's impossible. I will say most seismologists don't see it in the foreseeable future. So what you just described, a day ahead, is what we would call earthquake prediction. What I'm talking about is earthquake warning. And the difference is, for warnings, the earthquake itself has begun underground. So the earthquake rupture has nucleated on the fault surface, and that's why we're talking about seconds to minutes. To actually do that a day ahead, you have to predict when the rupture is going to start underground. And that's obviously a very different set of physics, very complex physics that most seismologists agree we're not going to be able to predict that in the future. Yep.
I just downloaded the MyShake, thanks for that.
Excellent.
But they also have something called Earthquake Alert. Is that something competitive, or do you know anything about that?
I can't remember. There are so many earthquake apps. There's nothing that does what MyShake does. I can say that much. I can't remember specifically the app you're talking about, to be honest.
It's got the same rating, that's all.
It's got the same rating? Oh, and I thought we had a good rating.
You do, 4.3.
Okay, 4.3. I'll explain what we're not doing with our app yet. We're jumping ahead a little here, but that's okay. Is actually providing warnings.
Oh, okay.
Now, when we actually start to provide warnings, either the rating could go up or it could go down a lot, depending on how successful we are, right? Yeah. But there are no other app that's trying to do what MyShake is doing right
So
now.
when are you going to start providing warnings?
Why don't you ask me that question at the end? Okay, and let me show you where we are, and then I'll... Sure.
You sort of set up a scenario where the earthquake starts somewhere on the fault and propagates along the fault. Is that the way we should all imagine most big earthquakes, or can there be some kind of random, not following the fault line kind of earthquake?
No, I mean big earthquakes, when I say big earthquakes, I mean something bigger than a magnitude 7. They have to rupture some significant length of fault to get to be that big, right? The magnitude of the earthquake is actually related to the area of the fault that's rupturing, okay? So once you get to about a magnitude 7, you actually have to have some finite extent. We think of them as being finite faults. You can sort of treat small events as point sources. And so it's quite possible they will rupture on an unknown fault. But for big earthquakes like that, we have no real evidence of, the whole question about how you create new faults, let me put it like that, is unclear. So for the sake of thinking about hazards in the future, we can think about big earthquakes rupturing on known faults. And then in other tectonic environments where the faults are buried, we may not be able to see the fault, we may not know exactly where the fault is, but we know the type of fault that's there. Yeah.
Since the faults are so localized, does it make sense to have sensors deep down instead of only on the surface?
So the Berkeley Seismolab runs seismic networks. Most of them are at the surface, but we do also have borehole sensors. But most borehole sensors are still just a few hundred meters below the surface. So that's sort of, I mean, it's good because it reduces noise, seismic noise on the sensor, but it's not like you're really getting that much closer to the fault. To give you some scale, in California, where the faults are strike-slip type of faults, for those of you who remember your plate tectonics, the plates are moving horizontally, and so we have strike-slip faults. The actual rupture extends from the surface down to about 10, 12 kilometers depth. Okay, so that's the fault plane, 10 kilometers in depth, and then up to hundreds of kilometers in length. So, you know, going down a few hundred meters, it's really just scratching the surface. Okay. Please keep them coming. That's great. Okay, so who would use earthquake early warning? Well, the idea is to reduce hazards, falling hazards. That's the ceiling tiles example I gave you, just to put some numbers on it. In Loma Prieta, 50% of the injuries were caused by these kinds of falls. In Northridge, again, more than 50% of the injuries were created by non-structural falling hazards. And so, two big ifs: if everybody receives a few seconds of warning, and if everybody uses it to take action, then you could reduce the number of injuries in an earthquake by 50%. Okay, and this is a big deal. Even in Northridge was not a big earthquake. Northridge was a moderate-sized earthquake. Most of the shaking was not in the urban environment, just like Northridge, just like Loma Prieta. But the estimated cost of just the injuries is $2 to $3 billion. So if we can halve that, that's a significant saving using early warning. But the other applications are automated control, slowing and stopping trains. Those of you who live in the Bay Area or use the BART train while you're here, BART already gets our warnings and automatically stops the trains, even though it's a demonstration system right now. So they are so concerned about what will happen to their trains, derailment type of scenarios, that they want to slow and stop the trains. Stopping elevators, it's estimated several thousand people will be trapped in elevators in the next big earthquake in the San Francisco Bay Area. Hazardous machinery, chemicals, data security, etc., etc. Just, I want to give you a flavor of why we're doing this. Yeah?
I was in Japan and met some guys who built the bullet train, the Shinkansen. They said that they never had trains jumping tracks, and they have done some amazing design of the system.
First of all, it's not true. They've never had trains jump the tracks. 2 trains have come off the tracks. But in both cases, it wasn't a catastrophic derailment. In both cases, they literally did just jump the tracks. And so there may even have been no injuries. So they do have, I don't want to diminish, they have a spectacular safety record. Part of it is that they have engineered the bullet train system to really withstand shaking in the first place. That's the equivalent of building buildings that don't fall down. The second piece is that they have early warning. Japan has a nationwide public earthquake early warning system. They've had it since 2007. The bullet trains have had it since they were first built in the 60s or 70s, I forget. And so as soon as they see any kind of earthquake that's going on, the trains start to slow and stop. Exactly the same reason that BART jumped on this as soon as we started to experiment with it. Okay, and then how will you get earthquake early warning? Well, one obvious way, of course, is everybody has one of these devices in their pocket right now. And so what
Earthquake,
warning
duck
might
cover
like
and
to be
hold
this.
on. Strong shaking expected.
Very simple message. Earthquake's coming, duck cover and hold on. An app that can show a countdown. There's this particular version. This is actually a real app, so I actually have this app on my phone. No, it's not publicly available. This is still a project we have test users like BART now, but it's not a publicly available kind of thing. But a small group of people get these kinds of warnings. This is feasible. Okay, we can actually do this. This technology exists. It's just about taking this and turning it into a full-blown public system. Again, this is the system using the traditional seismic network. We have apps for your computer. The whole idea is you would push this warning out through any kind of communication channel that you can. Yeah.
Can I point out that there were a small group and not public?
Absolutely you can. Okay, so the technology exists, and just to kind of conclude this, to show that this is possible, I'm going to have somebody else show you that the technology exists.
Very interesting.
Digital communications travel at the speed of light. Thanks to things like fiber optic cable, we can move information literally in a flash, and that is good, just in the abstract. But that is, it turns out, potentially life-saving. If the information that you are moving at the speed of light is notification that an earthquake is about to happen. Earthquakes happen in a specific place in the ground, right? Earthquakes have an epicenter. But you don't just feel an earthquake at the epicenter. The shuddering waves of motion in the earth from an earthquake, they emanate out from the epicenter of the quake, traveling at the speed of sound. So if you had the kind of motion sensors that detected earthquakes, if you had seismometers along fault lines all over earthquake-prone regions, when there was an earthquake, the seismometers nearest to the epicenter, they could register that an earthquake has happened, right, feel the shake, and then they could send a digital signal at the speed of light, notifying communities nearby that this traveling at the speed of sound tremor, this motion of the earth, is about to arrive. This is not a way of predicting earthquakes before they happen. It's a way of basically warning people that an earthquake has just happened and that they are about to feel its effects. Brace yourself. But this thing works. Scientists at UC Berkeley say that their Shake Alert Earthquake Early Warning Project, it set off an alert. It did go off this weekend, during this weekend's large quake in Napa, California. It was about to be felt in Berkeley, and this is the alert that told them so. Watch this.
Earthquake, light, shaking, expected in 3 seconds.
They got a 10-second warning that they were about to feel the quake. And 10 seconds is not much time, right? But this brace yourself warning system, it works thanks to the simple fact that the speed of light is faster than the speed of sound, and earthquakes only move at the speed of sound. With more sensors in more places, they could presumably deliver even more warning time. California's hoping to have that bigger system in place in the next few years if they can get it funded and finished. From the LA Times today, once fully developed, the system could give downtown Los Angeles 40 to 50 seconds of warning that the big one was headed from the San Andreas Fault, giving time for elevators to stop at the next floor and open up, for firefighters to open up garage doors, for high-speed trains to slow down to avoid derailment. and for surgeons to take the scalpel out of a patient. Giving your surgeon enough time to get the scalpel out of you before the giant earthquake starts shaking the operating room. That idea of a tectonically shaking scalpel inside your body somewhere, that is something you can never unknow, and I am sorry, but the idea that this warning technology, that it works, that it worked this weekend, in fact. It's not just on a drawing board somewhere, it is in effect, and it could be expanded and is being expanded. That is an excellent thing. They've got a system like this in Japan, they've got it in Mexico and some other places around the globe. California could get their whole statewide system done in a few years. God bless the geeks. They will save us all. Now it's time for the last word with Lawrence O'Donnell. Hi, Lawrence.
Rachel, I just want them to make the earthquake warning voice a little less scary.
Yeah, a little more soothing. Maybe with a little music or something.
Right.
Ding dong.
Yeah.
Thanks, Matt.
Thank you, Rachel.
Great little summary of what we're doing, except for his comment, of course. I think we want it to be scary. You want people to pay attention. But this, obviously, she put this together after the Napa earthquake. But again, this is just to kind of illustrate. I mean, it's great. You know, we spent, I don't know how many years trying to work on this project. And she condenses the value of it into just 3 minutes in a very entertaining and amusing way. It was a very, very nice piece. The point is, it works. Okay, we can do this, but of course, we would like it to be better than it is right now. Finally, before I start talking about the cell phones, to give you a sense of that traditional seismic network I keep talking about, these are the sensors that we use in Southern California, Northern California, Oregon, and Washington. And then we also stream data in from Canada and Mexico, for obvious reasons, to the north and the south. So right now, today, there's about 800 traditional seismic stations that stream their data in real time into our system. We detect earthquakes on individual waveforms. We recognize when we see clusters of triggers, we recognize those as earthquakes, estimate the location, the magnitudes, and push the warnings out. And the groups that are getting the warnings right now, there's about 75 institutions. It's probably closer to 100 actually now. But to give you a sense, emergency response groups at state, city levels, power, utility companies, BART, I already mentioned, biotech companies, Google, of course, they were one of the first groups that just wanted the data. Other Intel, Microsoft groups like this. So the point is that this system, this traditional system, it's coming, and I can tell you more. In fact, the governor has to sign the state's budget today, in case you didn't know that, very important. And in fact, that will include $10 million to start rolling out the public earthquake early warning system in California. Okay, so that's the traditional system, traditional network. This is what's next. And this is the piece that we're sort of struggling with when it comes to figuring out how to handle the data. And so, as you just saw with Shake Alert, the whole idea is that we would push the warning out to people on their cell phones. So that's obviously sending a message to you on your phone. The whole point of MyShake is we actually want to use the accelerometer that's in your phone to also detect the earthquake in the first place. So we want this to become the seismic sensor, in addition to being the mechanism by which we might push a warning out to you. So how would this work? Well, you have thousands, potentially millions of smartphones across an earthquake-prone region that are running the app, the MyShake app. And they're looking for trying to characterize the motion all the time. And when you see a cluster all recognizing an earthquake, we send that information to a server that's based in the cloud for real-time analysis, and we detect that there's actually an earthquake that is underway. Okay? And so this is the piece, as I said at the beginning, that we think will drive people being willing to run the app on their phone and put the app, for that matter, on their phone in the first place. But for us, the objectives are much broader. This is about collecting the data, collecting the seismic data, the actual acceleration data from the phone, retrieving that from the phones, putting it in storage, and then we can use that for all the kinds of research activities that we use traditional seismic networks for, and possibly many more, of course. It's a very different and much larger kind of data set. So that's the idea behind MyShake. Now, what are the challenges with this? There are some significant challenges with this. The first is that the most serious ground shaking, the most serious shaking, I should say, your phone experiences is not an earthquake. Okay, this is stronger than an earthquake shaking typically. All right, so the amplitude of the shaking that is observed on your phone during most earthquakes, at least, is significantly lower than what you subject your phone to every single day. So we have to be able to separate out earthquakes from all of the other shaking, the much more frequent shaking type of events. And so this is what brought us into this whole question of very different type of data analysis to what we as seismologists are used to. And so we developed this approach where it's basically a classifier analysis. We came up with a whole array of different characteristics. We identified the 3 characteristics on the acceleration that allow us to most clearly separate earthquake shakes, shown in red, from non-earthquake shakes, shown in blue, using a neural network classifier. And we do this on 2-second chunks of data. So this runs on your phone. It's analyzing every 2-second chunk of data. It's calculating these characteristics, seeing where it falls, and if it thinks it's an earthquake, if it falls into this region here, then it triggers, and it sends that information, just the trigger time and the location of the phone, to our central server. And it's remarkably successful. In our testing before we rolled out the public app, we found that it was accurate 93% of the time. So that's really very encouraging. This is just on one phone.
Yeah, what are the axes?
Okay, so the axes, IQR is interquartile range, and so this is essentially a measure of the amplitude. I'm sort of almost embarrassed to describe this to you. This is very basic. So this is just an interquartile range, and then this is the zero crossing, just a simple count of the number of times the trace crosses 0, basically a frequency measure. So this is a frequency measure, this is an amplitude measure. There's a third one. We identified the top 3, and I honestly can't remember what the third one was. It was significantly less important than these 2, as it turns out. Yeah.
This is for a single accelerometer.
Absolutely.
It's amazing, but I would think that the most useful thing would be the fact, for example, if all of us were to accelerate in the same way, it'd be that in fact the data from a collection of accelerometers would be much, much more valuable.
You are exactly right. Give me 2 slides.
Okay. What does 93% success mean? Does that mean what about false positive?
Yeah. No, okay. So the 93% success, so of course we did a whole bunch of tests. One test was we had a forerunner of this app on 75 student phones actually here on campus, and they had a very simple STA-LTA trigger algorithm. They were triggering all the time, sending 5 minutes of data to our backend server for 4 months. Big non-earthquake data set. So, and then we had, for the earthquake data set, we had 2 types of data. We actually put an array of about 20 smartphones on a shake table, an engineering shake table, what they used to test buildings, and recorded earthquakes. That was our earthquake data. We also took data from traditional seismic networks and degraded it so it looks more like cell phone data. We are adding noise, reducing the... And so the way we would develop this is that we drew data from both of those data sets for the classifier analysis. This 93% success rate, the 2 numbers were 93 and 96, and I may have the wrong way around, and I forget whether this is the 93% success rate on non-earthquake data and 96 on earthquake data or vice versa, but it doesn't really matter. What was another question?
Actually, it does matter, because if you have a lot more events that are sort of possible earthquakes than real earthquakes, then you want to be...
It doesn't matter, because the most important step is the next step. All right, and so if as long as we are doing a reasonably good job of recognizing it's an earthquake on the phone, the next step is the real determining step. That's why it doesn't matter. Okay. So to give you a sense, right, so the whole idea, this is on one phone. So your phone thinks it's seeing an earthquake, it sends the trigger to the central server. And just to give you a sense of what that looks like with the data, here's an example. This is a real earthquake. This is actually the Napa earthquake recorded on a phone. This is on a traditional network with phone noise added. But this just shows you the classifier analysis: no earthquake, no earthquake, no earthquake, 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 no earthquake. And then here's a much longer time series, 300 seconds. This is one of those non-earthquake samples, and it's classifying that it's not an earthquake for most of the time. Just to give you a sense. Okay, so now a phone thinks it's seeing an earthquake. We now need to confirm that earthquake is underway, and we do that by simply recognizing a space-time cluster. And this is even simpler, or even more embarrassing that it's so simple than the on-phone kind of application, because all we're doing right now is looking for a number of phones to trigger within small space and time being 10 kilometers, and I believe we're looking for within 10 seconds or 20 seconds to give you a sense, but that's all, very basic. But it actually works remarkably well. This is still a simulation. We actually have a public version of the app, and I'm going to show you data from that in a minute. This is from pre-release simulation of that. And again, this is taking traditional seismic networks. So this is, I'm going to show you data from magnitude 5 earthquake in the Los Angeles area. So this is the traditional seismic network that's been downgraded, but then we applied our algorithms to it. So we applied the on-phone algorithm to recognize when one of these simulated phones sees an earthquake, and then we apply our detection algorithm, which is very basic. And I'm just going to play this video, and you can see how it does. Yeah.
Is the energy drained from the accelerometer small enough that people can keep the app on all the time?
Great question, right? I mean, I'm a seismologist, and all of a sudden I have to worry about how do you get people to put an app on their phone. And the thing you immediately learn is that the key thing is it can in no way interfere with what people actually have the phone for. And the number one way that you do that is you kill their battery before the end of the day. So our design criteria was that the app has to, or should use, no more than the same amount of power that your phone is using when it's not doing anything, right? So when my phone's in my pocket, it's still doing low-level processes, and our design criteria was we wanted to be at about the same level. We actually didn't quite get to that point, but we did get to the point where most modern phones, for most typical users, you can be running this app on your phone all day, and you still just have to charge your phone once a day, which is what most people do, obviously. Yeah, but that's an area that we still actually want to reduce power. Okay, so let me run this simulation for the La Habra earthquake. When it turns pink, it's when a phone triggers. When the blue star appears, it's when the detection algorithm recognizes there was an event. It sort of moves around as it kind of relocates the event with time. I think the initial magnitude estimate was 5.0. I'll play it again in a second. It was 5.0. It actually does a remarkably good job. This was kind of our proof of concept stage of the whole project. Oh, here we go again. So the first 5 seconds, magnitude 5.2. And we can compare how this performance, this is again simulated performance, and so we can compare that to the actual performance of Shake Alert, the real warning system that I showed you a few minutes ago. And they're actually very similar, 5.3 seconds after the origin time, 5 seconds, magnitude 4.3, 5.2. So this is quite remarkable. This is why we decided to proceed. We feel like this system can actually do something similar to the traditional network. Yeah.
So is the information being sent from a phone simply 1 bit, which is I think I detect an earthquake and then give the onset time, the timestamp?
Yeah, there are 2 types of data that comes, actually there's 3 types of data that comes from the phones. When a phone triggers, it immediately sends, I've triggered, here's my trigger time, and here's my location. Okay, and some other, but you know. It records a total of 5 minutes worth of data. So it has a ring buffer of 1 minute. So we have 1 minute before the trigger and 4 minutes after. And then the other is a heartbeat information, sort of state of health. We need to know how many phones are live so that we can make this algorithm work. A key part to this is you need to know, you want some proportion of your phones to have triggered. So you made the comment, well, if everybody's phone moves at the same time in this room, well, that just means everybody stood up to cheer because I scored a goal, right? So this whole question about how you separate out real earthquakes from other kinds of activities like that is one of the remaining challenges, absolutely.
But this is based just on the fact that a trigger occurred, and now you're looking at just clusters of triggers.
Yeah, and so the other piece is, right, we're looking for a cluster of triggers in space and time, and we look for more than, I forget now, 50% of the phones that are active to have triggered. And that's why we need the heartbeat information, so we have some sense of how many phones are running this system.
But you're not using the acceleration traces.
No, because they take much longer. So by just sending that small packet of information, we get it in, for most cases, a few milliseconds. As soon as you start to send waveforms, it's slower. Although in the future, we might be able to.
Okay. So, going back to the original classification that each phone does, don't earthquakes come in have different features in terms of frequency and amplitude and so on?
They do.
Is there mean, you had this cutoff of this high frequency or something.
It's actually low frequency. It was long periods, right? It was longer periods to the right, and so it wasn't the highest amplitudes, but it also wasn't the lowest amplitudes either, right? So it was long periods and these intermediate amplitudes that are characteristic. So of course, there's some sensitivity here to the magnitude of the event. So this ANN trigger will only work, we would expect it to work for large events. We also expected it only to detect the S-wave arrival, that stronger shaking phase. But I'm about to start showing you data, and it's, well,
so going back to Dick's question, which is good about the power, do you have any ability in your application to kind of turn it off, put it quiescent for a while because you're burning too much battery?
Absolutely. So when, I forget what the number is, but when the battery goes below some level, it turns itself off automatically.
I mean, you have a huge sample potentially. You might want to turn a lot of them off just so that they randomly, so they save power.
So what I haven't said at all here is that this project is actually a collaboration between the Berkeley Seismolab and Deutsche Telekom. And Deutsche Telekom are interested in this. I think one of the official reasons Deutsche Telekom are interested in this is because they're interested in the whole networking problem. Flash mob type situation where you have a lot of phones that are all detecting and all want to send information, managing the network, turning phones on and off in an intelligent way for exactly the reasons you just described. That's right. Okay. This is just to show the sort of noise floor of the phone and compare it to earthquakes. So the dashed lines here are the typical amplitudes for different magnitude earthquakes at 10 kilometers. So magnitude 2.5 up to like a 6.5, 7.5. And then the colored lines are the noise floors of the phones. And so this is when we would, tells us what kind of earthquakes we would expect. And so again, our conclusion was that we would be able to record magnitude 5 earthquakes at 10 kilometers greater. Again, this was our pitch before we rolled out the app. We rolled out the app in February. I'm going to show you what we found since in a moment. This is what a traditional seismic net station noise sensor noise level looks like, so much lower, of course. But this is also another MEMS sensor. This is a very high quality MEMS sensor. I mean, we don't expect this to ever be in phones, but the point is we only expect the sensors to get better in phones. And so, whatever we can do today, we're going to be able to do more tomorrow. Usual refrain. Okay, I'm not going to go through this. MyShake isn't going to replace traditional seismic networks. I don't want people to think they shouldn't fund traditional seismic networks because we have cell phones. That would be very foolish, and so please nobody take that away from this talk. But the point is that traditional seismic networks only exist in a few parts of the world. Okay? That network I showed you on the west coast of the US, really there's only the west coast of the US and Japan that have networks like that. The majority of places around the world with significant seismic hazard, all of the red regions on this map, have very few traditional seismic stations, but I don't need to tell you how pervasive smartphones have become, and they're only ever getting more pervasive. This brings us back to this Nepal example that I showed you at the beginning. They had 2 magnitude 8-ish earthquakes last year, causing a lot of damage and a large number of fatalities. I actually tried to figure out how many seismic stations there were in Nepal, and the conclusion was there's about 2 plus or minus 4. Okay, it's incredibly unclear how many instruments there are in Nepal. However, it is clearly very small. All right, but there are 6 million smartphones in Nepal. All right. In Kathmandu alone, there are about 600,000. Okay, so again, this is kind of why we think there's real potential here. Okay, so this is where we are. You just downloaded the app. You obviously have an Android phone. So here's the catch. We only have it for Android phones right now. And the reason is that there are many more Android phones around the world than there are iPhones. It's just a question of resources to develop an iPhone version. Okay, so if you download the app today, you do not get earthquake early warning, just to be clear. Okay, what you do is you'll learn about the impact of past earthquakes. Hopefully we can help educate people so people will be better prepared for future earthquakes. So right now, this is a citizen science project, right? I'm asking you to put the app on your phone to contribute to the science that we're doing. There's no early warning right now, and so this is just running through what you can see. You get all of the kind of information you'll get from any earthquake app. You'll get from this app. The difference is that this app will also actually provide us with data about the earthquakes. And of course, obviously, the idea is that we can do something interesting with this now, but in the future, we could actually start to provide earthquake alerts. Okay. All right, so the launch. So that, we had it on, I think I said earlier, 75 phones, and we decided, okay, we should try and roll this out and see whether we can get any interest. So we planned a public rollout. We were hoping, we had it on 75 phones. We were hoping to get it on maybe 1,000 phones. We decided to plan big, so we got ready for what we thought we could handle 10,000 phones. And we rolled it out, and in the first weekend, we had 60,000 phones download. And with a completely global coverage, as you can see here from this map, we were just expecting to get interest in the US. So that was great. I mean, there was a huge amount of interest in it. This was back in February. So today, there are about 40,000 phones that have the app on them. And on any particular day, about 11,000 phones are actually communicating with our system, right? And this is 6 months later. So we're quite pleased with that, though clearly we have to start worrying about how we maintain this and potentially build the number of users. But this is actually the largest global seismic network by a long, long way right now. Yeah.
So of the 11,000, roughly how many are in, say, Bay Area?
I think actually I'm going to show you that. Hang on 1 second. I think I have a map coming up. So this is what the number around the world. United States is pretty high. We really wanted to have a big rollout in Japan because they have a lot of earthquakes, but we actually have a Japanese language version as well, but we're really struggling. It's sort of interesting. There's interest in some parts of the world and not in other parts of the world, so we're trying to understand that. Here's our answer for the Bay Area. So of the 11,000, about 1,200 are in the Bay Area and about 2,100 are in the Los Angeles area. And so here's, I don't know if you can read the numbers on this map, but so the red are the hundreds and the orange are the tens. I actually put this map together last week. And so this is actually the number of phones that were active on, I forget what day, Wednesday of last week. And then this is across the East Bay where we are right now. You can see slightly higher cluster in Berkeley, but not that much higher than everywhere else. So, we're really quite pleased, obviously. So now we're actually starting to get, yeah.
How many phones roughly do you need to have an accurate detection using the data?
So again, the real-time server, the real-time detection server, is now operating, but it's not working properly. We've run into all kinds of technical challenges. Okay, let me start there. And our first focus when we rolled it out was to deal with the technical challenges on the phone, not the technical challenges associated with the server. So the server is running, but it's not doing a very good job of detecting earthquakes at all. So I can only answer your question based on our simulations before the rollout. And based on our simulations, we estimated that you needed about 300 phones within a 100 kilometers by 100 kilometers area. So we clearly exceed that. But who knows? This is the real world, not the simulated world. So we suspect that we can do a reasonably good job with this number of phones, but we're just not at that. We've been clinging on by our fingernails since we rolled out, basically.
So this may be a long question, or answer to the question, but what are the technical challenges you've run into? I mean, maybe it's too long. It's like going back and starting seismology all over again. The first thing we all had to relearn is time really matters. Okay, and so getting as accurate time as possible, timestamps on the waveforms that were coming in, and the triggers for that matter actually, was quite a challenge. And it's surprisingly difficult to get reasonably good times. When I say good times, we're used in seismology to having things accurate within a few milliseconds. We're not going to get that kind of accuracy. But we've had all kinds of issues with timestamps being off by hours. I mean, all kinds of things. I mean, not complicated stuff that somebody with the right technical expertise and just having the time to put into it can fix. Those kinds of challenges. I'm going to show you some of the data. So we're now at the stage where we are collecting large volumes of data, and so we can start dealing with some of the more real challenges where we want to develop the real-time detection algorithm to work properly. We want to do a better job of triggering on phones. To give you a sense, a typical phone will trigger about 4 times, on average, will trigger 4 times a day. So 4 times a day, the phone thinks it just saw an earthquake when there was no earthquake. Okay, so the phone, of course, is filtering out by the majority of the events, but still we get 4 triggers from every phone. We have 11,000 phones, and so those are the kinds of issues that we're working through. Okay, 5 minutes, yeah.
You didn't mention it, but you're probably not the first one to think about it. You probably make a lot of money if you can predict the 10 seconds, especially if you call your broker and only then update the applications.
Yeah, I mean, yeah, I think there's a lot of applications for earthquake early warning, is the answer.
Good sponsors you can find there.
Okay, so just to give you a sense of some of the data, it's kind of how I want to wrap up is just show you some data. So since we rolled out, I put this slide together a few weeks ago, but we've recorded probably about 150 earthquakes at this point. If you remember, I said we were expecting to be able to record magnitude 5 earthquakes. We're actually recording down to magnitude 2.5 earthquakes. So we're really quite pleased with that. I'm just going to show you. So I'm sort of assuming people understand what I'm showing when I show this. This is an acceleration trace. So the accelerometers in your phones have 3 components. Two components in the plane of the phone and 1 component perpendicular to it. And so this is just the output, the acceleration as a function of time. This is actually the smallest earthquake we recorded. This is a magnitude 2.5 on a phone that was very close to the earthquake. And you can see the signal to noise ratio here is terrible, but still the ANN algorithm detected that this was an earthquake. We literally have this one trace from this earthquake. But this is just to show you the lower bound in terms of magnitude and the upper bound in terms of bad data, okay? Or poor quality data, I should say. We've been surprised at how many induced earthquakes we've been recording in Oklahoma. You may be aware in Oklahoma or Texas, other oil-producing areas, they're having a lot of issues with increased seismicity. There's nobody from the press here, so I will just call them induced earthquakes. And so this is one example of an induced earthquake. This is a very small magnitude 2.6 earthquake. One of the issues is there's almost no seismic networks in these parts of the world because there aren't any tectonic earthquakes. We have hundreds of phones recording these earthquakes right now. It's I'm waiting for the shoe to fall on that one.
Are these because of fracking or just regular oil?
Yeah. To be clear, it's not the fracking that causes the earthquakes. When they do fracking, it's taking the fluids that they use and they pump them down into waste wells, and that's what causes the earthquakes. Exactly. Yeah. Okay, so this is the magnitude 2.6. Magnitude 5.1, this is kind of interesting because we also only ever expected the algorithm to trigger on on S waves, the larger packet. This is the P wave. You can see this is 1 bit, right, of signal. So this is a very low sensitivity instrument. The 0 time is when the phone triggered. So the 0 time is when the phone triggered. We then went back and we identified the earthquake, and this is the predicted P wave arrival, the predicted S wave arrival. So this is a magnitude 5 event that the phones are detecting, and we're actually detecting the P waves. We never thought we would actually be able to detect the P waves, and we are. Yeah.
It seems that your triggering algorithms are not bad. Do you really need algorithmic innovation?
I think that let me answer. I have a slide at the very end where I'll answer that question, if that's okay. But let me keep going. This is Ecuador. If you may remember, there was a fairly damaging earthquake in Ecuador. We didn't have a huge number of phones. This is our cell phone map for that day in Ecuador. The red dots are the phones that were active, but they weren't steady. So the phones, when they're active, they wait for the phone to be steady, i.e. you put it down. And then they start monitoring for the earthquake. And so the red ones were not in steady. The orange were in steady but didn't trigger, and the greens were in steady and did trigger. So we just had 2 phones trigger for this particular earthquake, but there's quite some distance away. This is the trace from one of those, and it's kind of really interesting. So again, the trigger is the 0 time. Okay, the green is the predicted P wave arrival, and the red is the predicted S wave arrival. So what actually happened here is, and then this is the person picking up the phone. So what actually happened here was the phone was sat on somebody's desk, it triggered on the earthquake, it recorded the P wave arrival, it recorded the S wave arrival, the person felt the earthquake and picked up their phone. Okay, so this is them picking up the phone. So if I zoom in, so P wave arrival. If I zoom into this region here before they pick it up, just so you can see the data. So this is when the phone triggered. This is the P wave arrival in green, and then this is the S wave arrival, and then they picked it up. Okay, and then let's just go through the rest. So Alaska, these are just more events from around the world. Taiwan, Argentina, Japan. I mean, just a massive amount of data that we're now just at the point where we can start thinking about what we want to do with it. Mexico, Nepal. Okay, I'm going to finish by showing you this. This is our best event so far. This was actually not long ago. This was just a few weeks ago, June 10th. This is a magnitude 5.2 earthquake in Southern California. And so the star here is the location of the earthquake. So unfortunately, I'm a seismologist, unfortunately the earthquake was a long way away from anybody. And so the closest phones are like 20 or 30, it's only a 5, it wouldn't have hurt anybody. So the phones are 20 or 30 kilometers away. Again, same thing, green ones are the phones that triggered. A total of over 700 phones triggered, 600 uploaded waveforms, and of those 600 uploaded waveforms, about 100 were good, as in we can actually see the earthquake. We would actually consider doing something with those waveforms. That's what we mean by good. Just shows you, these are the trigger times of the network, the ANN trigger times. The blue is the P wave arrival, the red is the S wave arrival. So you can see that a lot of phones triggered on the P, a lot of phones triggered on the S, and then there's some other, this is probably just triggering on the shaking after the S wave arrival. This is the data going out to about 180 kilometers. You can sort of see the P wave arrival, you can see the S wave arrival. So we're really pleased. I mean, this was just a few days ago, right? So this project is really just getting going. And this is more data than we have from an earthquake across Southern California at this point. And then this just shows you the peak amplitude. One of the issues you look at with buildings is the peak shaking. So as a function of distance, this is distance. This is the peak ground acceleration. Obviously, the acceleration goes down as you get further away. The red are the traditional seismic stations, and the blue are the smartphone stations. And so, the data's consistent. I mean, we're still in that stage of verifying that we understand what the data is showing us. This is an example where there was a phone, I think it was a kilometer away. Yeah, a kilometer away from a traditional seismic station. And you can see that they're slightly different. That's not surprising. They're a kilometer away. It's very similar data. So we feel like the quality of the data is pretty good. Okay, so to Dick's question, what's the real challenge here? It's sort of, as I was thinking about this morning, I mean, the reality is that the challenges are still the same challenges that we've always had with seismology. It's just we have to do an even better job than we've done in the past. The first is triggering on earthquake signals. So Dick asked, it doesn't seem like you have a problem triggering. But the issue is that we do have, as I mentioned, in this case, we have every phone triggers on average 4 times a day. When you have a lot of spurious triggers, periodically you create a false event. We see that with shake alert as well, the traditional seismic network. So doing a better job of recognizing that this is actually an earthquake. I picked this one because it's not a high quality data, it's not poor quality data. The signal to noise of the P wave is 2, the signal to noise of the S wave is maybe 5. Doing a better job of recognizing that that's an earthquake and not a bus clearly will make a big difference. And then the other piece, of course, is associating these clusters of events. The reality is we don't know, I forget who asked the question, we don't really know how well our real-time detection algorithm is working right now, just because we've not yet had the chance to really assess that. Clearly, it's not going to be working very well. I'm very confident of that. And so quite what the path forward would be, but we need to do a better job of being able to recognize these earthquakes. When it comes to early warning, it's about being able to use as few stations as possible, as close to the epicenter as possible. And what's interesting, as I was putting this together, it's exactly the same 2 questions, whether we're talking about shake alert or MyShake. I actually have a postdoc right now whose job with shake alert is to develop an earthquake classifier for the traditional network, right? Very similar perhaps to the earthquake classifier we developed for MyShake. So it doesn't matter whether it's the high quality data, the low quality data. It's the same kind of challenges of better earthquake detection and then better clustering analysis that we need. But obviously the potential here for what we can do is really very exciting. Today of all days, it's a nice day to show this slide because, as I said, the governor's about to sign the budget, which will be the first California public funding. Congress actually started funding a public early warning system in the US 2 years ago. We've had 2 rounds of funding from Congress, and the president put his support behind this earlier this year, also in February actually, by hosting an event at the White House to promote shake alert. So I can stand here actually today, this is very different, and actually say I'm very confident that we will have a public earthquake early warning system on the west coast of the US in a few years because the funding is coming, the network exists. So that's coming, so that's good. Of course it could be better, but it's definitely coming. And then of course with MyShake, if we can push this through to its conclusion, we could potentially be doing this all around the world. And so I want to draw a clear line though. Shake Alert I call a proven technology. MyShake is a research project. So that's a very important distinction that I think everybody here understands. Okay, thanks very much. Be happy to take questions. Yeah.
Have you just considered lobbying the telephone carriers to put it on cell towers? Because you'll have just the density you mentioned earlier, 300 per 100 square kilometers. There's more cell towers than that, increasing.
You mean the detection algorithm put it on cell towers?
Because lobbying those guys is just 3 or 4 of them, right?
Yeah, they're surprisingly difficult to persuade to do anything, including, for example, delivering alerts from Shake Alert. We have talked to cell phone companies about doing a whole variety of things, and we've gotten nowhere. Deutsche Telekom, of course, it's sort of, it's the parent of T-Mobile. But even though Deutsche Telekom has gotten very interested in the MyShake project, getting that to translate to actions from T-Mobile has been almost impossible. Yeah.
Seems like it's just coming back to Stephen's point. If you, instead of just sending an alert, just send a short snippet of at least some encoding of the recorded data, and look at the correlations across phones, and you could get.
Oh, to improve the you mean, so you're saying you would expect the waveforms to look similar on multiple phones? Exactly. Yeah, so there's...
Not the waveform, because you don't want to send you don't upload 5 minutes. You upload 20 doubles, 20 floats. 20 floats would be a high level representation of a signal you're looking at. It's a thing right before your last classifier, which is earthquake or not.
Yeah.
Right.
If you upload that,
you
would do a lot better.
You could extract a...
So wait a minute, let me make sure I understand. You're not saying the waveform, the G, the acceleration. No. You're saying just the characteristics of the value of the different characteristics.
No, actually, 10 very well chosen doubles.
Okay, I see.
Okay, so it's a low dimensional embedding of and it's whatever your network is already trained against. At the last level, it's going to come down to 10. Make it 100, doesn't matter, but that's a tiny little packet.
Right.
And then, use the kind of coding techniques that are used for speech coding, right? Just extract a small number of parameters of the waveform, and that'll be enough to be able to detect correlations across cell phones with probably very little data, and you would get essentially, I think you could make this perfect.
Sounds great. Don't go anywhere. I need to talk to you.
I think I missed this. Do you use any time correlation between these signals, between the different phones to kind of see the wave?
We're not right now, and part of the reason for that is the timing. So still the timing, the uncertainty in the timing can be up to a second or two.
Do you have the access to the local time on the phone?
Yeah. Oh yeah.
They're pretty well synced. Can you use that?
So they're not actually. I know this has been part of our learning curve. They're not particularly well synced. The up to a few seconds is the ones that we believe are reasonably well synced, but we're still getting that kind of variability. We're still working through the problem, so I'm not going to... But
Sorry, GPS, if you have your GPS on,
No, it's not GPS. So to use GPS, right, it takes time. Your phone doesn't have its GPS on all the time. If it did that, battery would be completely dead.
So do you have it on?
But they don't.
Okay, but if they do.
Well, no. Even if your GPS, the GPS is on my phone right now, but the actual antenna is not trying to use the GPS signal, right? So your phone makes intelligent choices about when to go and get that GPS signal, but it then takes some time to get the lock and etc. So for the trigger, we can't wait for that GPS lock. That's the issue. So that's why we can't use GPS time. Yeah.
So I would conjecture that the poor clock synchronization you have is because you're using Android phones. Seriously, because it's multi-vendor.
That's right.
And that if you went to iPhones, I think you could probably get on the order of a tenth of a second.
That's an interesting point. No, that makes complete sense. One of the big issues, we picked Android because there's so many more Android phones than there are phones around the world. However, the issue is exactly what you pointed to. There are also so many different types of Android phones, and so that's one of the issues.
Not all using exactly the same clock.
Yeah.
If you look at AT&T.
very different direction here, but do you hope to learn something about seismology from
Yes, thank you. I'm a seismologist, so yes, that was my objective. And instead I'm learning about cell phones. But no, I mean, so the kinds of things that we think that we can learn about, right? There's the I work on earthquake early warning, so that's what motivated a lot of this. So clearly we could do earthquake early warning with this. But I also think that we can understand much more about the earthquake rupture, for example. The understanding how take that magnitude 8 simulation I showed you at the beginning of the cartoon, actually understanding how that rupture propagates along the fault plane, the energy that's associated with each part of the rupture. We actually have very little information because we have very little data. So that's an example of if we had a rupture, of course, it would mean we'd have to have a big rupture going right through an urban environment, right, in order to have the right kind of data. But we would learn a huge amount about earthquakes. At the same time, we could learn a lot about the buildings that we're living in. Yes, we have good buildings, but there's a lot that's not known about how buildings respond to earthquakes. Imagine a skyscraper where you have, 100 people on every single floor recording the shaking. You'll actually be able to recover the normal modes of the building, things like that. You might be able to see how the normal modes of a building change over time because the building is being damaged by earthquakes, things like that. So yes, I think there's a whole array of things that we could learn. But right now, it's about actually trying to build the network. I mean, it's like going back to when people were first designing and creating seismic instruments, and you had to have good time, and you had to have accurate amplitudes, and that's where we're at right now. Yeah, absolutely.
So I actually I looked at your MyShake thing, and it has a weird statistic that the 1906 earthquake in San Francisco was 7.9, but at our location here, it says it's a 9. Do you have an explanation of that?
Oh, no, I know exactly. So it's, first of all, which earthquake? 1906? 1906. Yeah, so the 1906 earthquake was a magnitude 7.9 earthquake, okay? But what it's telling you is that at our location, the shaking intensity was 9, right? Yeah. So earthquake magnitude, there's one number for an earthquake. It's a magnitude 7.9. But then the amount of shaking you experience depends on where you are with respect to the earthquake.
So why was it worse here than over there?
No. These are different scales. Magnitude scale and intensity scale. So you're absolutely right. The intensity can only have been higher closer to the fault. Yeah. But here it's an intensity 9. Yeah. You see?
Okay.
Success. Okay, thank you.